Hello and welcome to Telefunken. In today's video, we're going to be fixing an ARP Odyssey. The original ARP Odyssey was manufactured from 1972 to 1981 and has been recently reissued by Korg. The Odyssey came in one of three cosmetic flavors, each housing a different array of circuit boards and filter combinations. The instrument that we're looking at today is a Mk II, or more precisely, a Model 2815, manufactured around 1978. The instrument comes with a lot of history as it was owned by a recording studio and never gigged. It is in great condition. However, it's broken and hasn't made a sound in years. We know that at least 2 sets of technicians have examined it and conducted quite extensive servicing. The latest including replacement of all the sliders, switches, socketing and replacing all the DIP ICs, including all the op amps which are notorious for breaking down, rebuilding and upgrading the 4075 filter using the Synth chaser kit. All the keyboard bushings have been replaced in an extensive keyboard servicing, and the instrument has been recapped, replacing the electrolytics and tantalum capacitors, and even replacing the precision resistors with modern equivalents. Still, in spite of all of this attention, there's been no sound from the instrument. I've had a look inside the instrument, and from what I can tell, all the servicing that has been performed well. The soldering is very neat. There's no damage to the instrument that I can see, and it's obvious that someone's taken a great deal of care. So why is it that I think I might be able to fix this? Well, sometimes problems benefit from a fresh pair of eyes. And although I'm not a professional technician, I'm a synthesizer enthusiast, perhaps that fresh enthusiasm will make up for a lack of formal training and experience. So I hope you'll join me, follow along as we explore the ins and outs of this Odyssey and see if we can bring it back to life. The approach that we're going to take is to remove all of the printed circuit boards from the chassis and place them in a wooden jig that will allow us to examine both the foil side and the component side of the boards at the same time. I know that this was not done by the previous techs, but it might be helpful, especially if we need to swap out individual components in order to test the performance of the instrument. We'll power it up, assuming it's safe to do so, and then go through the individual test points that are described in the service manual. We'll find out what's working and what's not, and presuming we can find the fault, we'll fix it and then address any remaining liabilities that might exist. A map and description of the ARP Odyssey test points is available for download in the description of this video. As well, I have another video on my channel which will walk you through each test point and show you the results that you should be expecting to see if your instrument is functioning properly. Okay, this is our next victim on the bench. This is a ARP Odyssey, ARP II, and we're looking at the underside of the instrument. The enclosure has the base of the instrument has been removed. What this does is it exposes the internal architecture, which we'll discuss just briefly. I've purchased this instrument from a technician in the United States who is apparently the second technician to have worked on the instrument. So we have, for example, new old stock capacitors on the power supply. These are 470 microfarad caps, replacing the smaller capacitors, which are fitted with the instrument when it leaves the factory. I believe the original caps are 220 microfarads, if I'm not mistaken. All the sliders have been replaced, all the keyboard bushings have been replaced. This is a tremendous amount of work. Many of the tantalum capacitors have been replaced. Here are 2, I believe these 2 have been replaced on the power supply. And what we can't see are all the components on the other boards that have been replaced. So the structure of the instrument is such that it is split into 3 main PCBs, A, B, and C, a connector PCB, which plugs onto the back of these 3 PCBs, and then the power supply is yet another printed circuit board. So I guess there are really 5 PCBs that we have to contend with here. We have essentially a linear power supply with a transformer converting the AC to the line AC to a lower voltage, which is then filtered and then rectified through a bridge rectifier comprised of these 4 diodes here. and then regulated. So we have a positive and negative 15-volt power supply, which is then distributed to the boards independently. We have also on the opposite side of this board, which is board C, we have a module which is attached to these 10 pins here. And this module is the famous ARP filter module. So ARP made 3 different modules for the VCF of the ARP Odyssey. And I believe this one has the 4075 module, which again we'll delve into in greater detail later. And in fact, it may be that this module is the element of the instrument that is failing. This is a 2-bus keyboard version of the instrument. You can tell that from the 2 bus bars here on the keyboard. And these are the J wires that when one presses a key, it results in the bending of these wires which come into contact with the buses independently. And one is a trigger, and I believe the other is measuring the control voltage. And then there's a 3-bus version of this keyboard assembly as well. I believe that the second is a trigger. And again, we'll investigate that in some more detail. I do note that there's a single unattached wire here, but that's just a ground wire for this keyboard. I doubt that that is the cause of our problem. So in order to diagnose the problem with this instrument and address it properly, I'm going to need to remove all of these PCBs from the chassis and then hopefully reconnect them in such a way that I can test them and determine how well they're working with one another. They're currently mounted onto the metal surface of the instrument, and the components are in between the PCB and that metal cover, and I need to remove that metal cover. So I'm going to attempt to fashion some sort of jig that I can use to hold the PCBs, keep them off the bench, and allow me to access either side of the PCB so that I can diagnose what's going on here. So I'll go to the drawing board and be back soon. So I have the ARP Odyssey set up on a jig that I have made to house the individual circuit boards once I've removed them from the instrument. And in order to do that, we need to do a few things. We need to disconnect the keyboard and remove it from the instrument. And that gets us access to the remainder of the bolts that are holding the PCBs onto the metal chassis. So that's step number 1, is to take this connector and gently move it from side to side while lifting, and this is J2 on PCB A. Disconnect this, and I'll also disconnect the PPC assembly, which in this instrument has been connected with this connector. Normally they're hardwired in, and then I remove the 4 bolts that are holding the keyboard assembly onto the instrument. These are really just machine screws. I'm using a 1/4 inch socket to remove these. And with that, the keyboard assembly can be removed. There it is in all of its glory. A Pratt Reed 2-bus keyboard, 4 volts per octave synthesizer. In order to remove the printed circuit boards from the Odyssey, we need to take out a number of screws which are in the corners, but there are also screws in the center of each PCB, affixing it to the metal chassis by virtue of standoffs that are actually welded onto the chassis. And so we'll remove these. So that's all 4 from each of the 3 circuit boards. And then there are these ones mounting each board in the middle. This one's a little hard to get at without removing this board. There, so we have 15 screws that we've removed. Now we need to undo all of these connectors. Each board is powered individually by these connectors that have the red, purple, and black wires. The other connectors are typically interfacing with the rear panel of the instrument. or in the case of this connector here, J2, this is of course the keyboard that we just disconnected. This is the connector that connects to the PPC, normally hardwired in, but thankfully whomever installed the PPC or serviced this last put it in this connector. And once we have all of these off, we should be able to lift the instrument or the printed circuit boards away from the instrument, which we can do either with or without disconnecting this circuit board, which holds all of these boards together. And I'm going to do it in this case without disconnecting this board. In fact, I'm going to use this board to lift out the printed circuit boards, and they all come out in one assembly, as you can see here. But we have to be very careful because they're only very loosely attached. So I'll set this aside until I can move the chassis. So I'm going to move the chassis into an orientation against the back wall of my workbench, like so. And what this will allow me to do is utilize the power supply in the instrument to do my testing if I so choose. Now, the jig that I've made has the ability to utilize external power, so it remains to be seen whether or not we'll use an external laboratory power supply or if we'll rely on this one. So the printed circuit boards actually sit in this jig in this position here, and you'll see that there are little cutouts, or you will have seen that there are little cutouts on the other side of the jig for any of the components that sit on the surface of the printed circuit boards, so they're not going to get squished. And then I can simply use these screws to hold these boards in place while I undertake the servicing. They're probably a little bit overkill, but they'll suffice. We want to be careful not to squish these printed circuit boards. There's no need to clamp them down too tightly. There we go. That's relatively secure. Not quite as well supported as it was in the instrument, but it will suffice. So now we see that these three power connectors can be connected to their various connectors on the PCBs. And on this instrument, they're labeled, which is quite helpful. And we see this one is so-called D, which is over here. If we examine the interconnect diagram in the service manual of the Odyssey II, we'll see that the CV out from the summing amplifier leaves printed circuit board A2 and comes out pin J4 pin 2 and then comes back in J4 pin 3. And so we need to jumper these pins, and they are here. This is J4 and we're jumpering 2 and 3, this pin and this pin, and I have a made up jumper right here. There we go. And that will take care of that and make sure that the CV path through these printed circuit boards is retained for our analysis. By marching through the test points, we can find out what parts of the instrument are working or not, starting with board A, which brings in the keyboard CV, generates gate, trigger, and noise signals for the rest of the instrument. Board B is where the actual oscillators are found, and we can examine whether or not they're generating the sawtooth pulse waveforms that we would expect. Board B also houses the LFO circuitry and the sample and hold. Board C houses the voltage-controlled filter, voltage-controlled amplifier, and the two envelope generators, the ADSR and the AR. I'm not going to go through each test point individually, as that's well covered in my other video, but we will be joining in the diagnostic process at the point where we've discovered a fault. If you're curious how we got there, please refer to the other video. By applying the approach described in the other video, we're able to determine that boards A and B were functioning perfectly, as all test points yielded the results that were expected as per the service manual. However, when we got to board C and examined test point 2, that's where things went off the rails. Test point 2, which should be the VCF output, yielded no results. It appeared as if the signal coming from board B was entering board C just fine, but once it entered the filter, it wasn't coming out the other side. So we then turned our attention to the schematics. The description of the voltage-controlled filter in the ARP Odyssey service manual is minimal at best, where the module is simply described as M1, the VCF module. This is a reflection of the secrecy and intrigue that surrounded the design of voltage-controlled filters at this time. Both Moog and ARP famously patented their filters, and ARP has been accused of copying Moog's transistor ladder filter design. Early versions of ARP Odyssey filters were potted in hard epoxy, making them essentially impossible to service. Later, they moved to a more pliable silicon encapsulation, and the filter in this instrument, the 4075, is unencapsulated. However, what little description there is of the ARP Odyssey filter in the service manual does allow us to identify the input, the output, and the power supply rails. By taking a systematic approach to this diagnosis, we know that in spite of the fact that the oscillators are operating properly and sending signals to board C, the voltage-controlled filter is not providing an output. So the first thing I've done is examine whether or not the filter is getting the appropriate power by measuring the -15, +15, and the ground at pins 8, 6, and 7, respectively. To my surprise, I measured +13 volts at pin 8 on the VCF module, which is supposed to be the negative supply rail, -15 volts. However, if I measure the power coming into board C2, I find that I've got a perfectly functioning negative and positive power supply rail. If I extend that analysis to measuring the input to the various integrated circuits on the board, I see as well that they're all getting both positive and -15 volts where they should. So why am I measuring +13 volts on pin 8? What could be going wrong? Even though ARP was reluctant to release the schematics of their filters, they've subsequently been reverse engineered and are available online. We can see here that the negative power supply enters by pin 8 and is then processed by a so-called supply conditioner, which prepares a -14 volt power supply for the LM3900 Norton OTA. While there are a number of things that could be going on here, my initial hypothesis is that some dysfunction, probably a short of some kind, is providing +15 to this negative supply rail, and that is translating into the elevation of the negative supply to +13, which we're measuring on pin 8. In order to determine if this is indeed the case, and to satisfy my curiosity about the work that's been done on the 4075 filter, I've decided to remove it from the instrument. Here we are at the ARP Odyssey Mk II, and we have, insofar as we understand and or believe, isolated a fault down to the VCF module, and this module is installed on board C, and it's installed using these pins, these 10 pins, which extend through the board and are soldered on this side, the back side of the board, and then the module itself is on the other side, obviously. And so in order to service this module, we need to desolder it. And so I'm setting about to do that, being mindful that these traces are about 40 years old and they're notorious for peeling off the board. So I'm going to start with a rather minimal solder temperature with a view towards being as gentle as possible to this board. And specifically, I'm looking at a solder temperature of 320 degrees Celsius, and we'll see if that is adequate to remove this. I'm going to be using solder wick because I find that this is the gentlest way of removing solder. And I've already applied a little bit of extra rosin to the joints, the solder joints. We'll see how that affects our ability to remove the solder. And it is indeed melting at 320 degrees, which is great news. Try to remove all the solder from the pin so that the pin is moving freely. And I can see it moving. I don't know if you can see that. It's wiggling freely. And so that one is ready to go. Next, we'll just move on. This next pin is a little more challenging for some reason. There we go, getting good flow. Okay, and we seem to have a free pin. Great. 2 down. And that's free. 3 down. A lot of solder on this guy. Let's see if we can, yeah, and this one seems to be free. This guy's loose. This guy's loose. 4 more to go. There we are. One's loose. Just 3 more pins here. So we're doing great. No evidence of torn pads. Solder flowing quite nicely. I believe that's due to the fact that this board has indeed been serviced before. So the old solder has been removed once in the past. There we go. That pin is free. 2 more. There we go. Guy seems loose. Is he loose? Yep. And 1 final pin. Pin 4. And that pin seems loose as well. There we go. So, if everything is right in the universe, we should be able to remove this module without any distress or stress on the board. It does seem as if we have a bit of extra solder here, so let's get rid of that. Seems free. Okay, that will be the module released, and we'll just do a little final cleanup on these pads gently. We do have a couple damaged pads, but they are workable. Number 3, number 1 are slightly damaged from previous extractions, presumably, but not so bad that they're not serviceable. And this is flux remover. Trying to scrub in the direction of the traces so as not to end up lifting any of these off the board, and in locations where they have torn a little bit and lifted off, I'm trying not to brush against the torn edge, so I'm brushing in the direction of the tear. Again, doing everything I can to minimize the potential for incurring further damage. So that's how much flux came off there, and that should give us a nice clean surface to solder onto. And we put this back. Don't need this label for this test point. It's well marked on this board. This is this one. And here we are. This is the VCF module from an ARP Odyssey. This is the 4075 module, and we can tell that it has been serviced. There's a number of bits of evidence suggesting this, quite a few actually. Amongst them, the fact that the LM3900 quad op amp has been socketed. Another, the fact that the capacitors have been replaced with Nichicons, the electrolytic capacitors. There are 4 of these here. We have other capacitors installed here, and they appear to be new as well. We have a number of new resistors and new transistors. So almost everything in here, except for this exponential pair, seems to have been replaced. So we've removed the filter from board C2 in order to address this anomalous finding where we see positive 13 volts at the negative supply pin 8 in spite of providing 15 volts to board C2. By removing the filter from board C2, we can isolate it and power it up using a lab power supply by connecting plus 15 volts to pin 6, negative 15 to pin 8, and see where things are going wrong on the filter board. Well, maybe I shouldn't be surprised, but there's nothing going wrong on the filter board. After powering it up, I see exactly what we would expect if it was working properly. Plus 15 is appearing where it should. The negative 14 volt conditioned power supply is working exactly as it should. And there are no spurious readings anywhere on the board that I can see. So what the heck is going on? Where's that positive 13 volts coming from if it isn't coming from the filter?
I'm attempting to show you something, and I hope that the filming is going to work so that you can see what I'm attempting to show you. But you may or may not be able to see that there's essentially a dry joint or a broken trace right here. And this is coming off pin 8 from the VCF module. And pin 8 is the negative supply. And it's supposed to have been supplying minus 15 volts to the VCF. However, if we measure the resistance from here to here, we see that we have essentially a connection. We're measuring essentially a short. And if we measure the resistance from here to here, we're measuring approximately 83K kiloohms, which is roughly the resistance across this potentiometer. The potentiometer from here to here, I believe it is. The VCF cutoff trim pot is approximately 100K. So we have a loss of connectivity from here to here. And if we measure the voltages, if we supply power to the instrument, which I'm about to do. Okay, we have power on now, and we're now going to look at the voltages. We see that here we have negative 15 volts, which is what we want. And here we have 13 volts, which is clearly not what we want. We want negative 15 volts. And so we need to fix this trace. So let's set about doing that. We'll just turn everything off, put our wrist strap on. We've got the soldering iron is hot, and frankly, there's probably plenty of solder right here. Let's see what we can do. I'll try not to obscure the view too terribly much. Okay, I'll turn the power back on. We have negative 15 volts here and negative 15 volts here. Great, so we have repaired this trace. I'm almost tempted to put in a jumper wire because I don't want this trace to be breaking off again, and potentially a jumper wire from this point here to this point here would do the trick. On the other hand, this is a somewhat sensitive part of the board. We don't want to be disrupting too terribly much if we can help it in terms of adding additional noise and the like. So I think we'll leave that there for now. Okay, so we have repaired a broken trace on our ARP Odyssey. So we'll take this filter, which I have examined by hooking it up to the power supply, and it appears, as best as I can tell, to be working properly. The power rails are all okay, and I have no reason to think that the op amp, the LM3900, is damaged. It's been replaced previously. The Tempco appears to be within specification. And so I'm about to solder this back into the board. It goes in this orientation on the other side of the board. So I'll tip the board up and see if I can install it and then get it soldered. Okay, so I've just reconnected, or rather inserted, the filter board, and you can see its pins protruding here. It moves quite easily, and if I pull it up all the way, the components on the other side are pressing against the PCB, which I do not want, because I'd like a little bit of space there for circulation. And so what I'm doing is I've pushed it down so that there is a space between the components, but it's not protruding beyond the slider potentiometers, which would be close to the surface of the chassis. And so it's at a location where it should be safe to solder in place. So again, using a soldering iron with a relatively low temperature, 320 degrees, and we'll set out to resolder this. Okay, now that I have a few pins connected, I can remove this. So we'll just make sure that we have good connectivity. And again, this is the trace where we had a bad connection. We weren't making it from here to here, and we resolved that. So we'll power this up and see how the instrument is behaving.
So when we put the filter module back in the synthesizer and we power it up, this is what we get at the output of the filter: an ascending sawtooth wave centered on 0 volts. This is not quite what's described in the service manual, as there are some errors in this section of the service manual, and those are covered off in the other video that I've already alluded to. So by taking a structured approach, marching through the test points described in the service manual, we were able to isolate the fault and fix it. This fault remained undetected after several inspections by both myself and other technicians, and it was only using this approach that I was able to isolate the specific area that was giving us trouble. Was it necessary for me to remove the filter in order to identify the specific location of the fault? Probably not. On the other hand, it satisfied my curiosity about the modifications and improvements that had been made to the filter, and I was able to confirm that the Synth Chaser 4075 filter kit had been installed properly. At the beginning of the video, I alluded to the fact that there might be other improvements that I would be making to the synthesizer before I buttoned it up, and those of you with keen eyes may have already noticed earlier on that I had rebuilt the power supply prior to the diagnosis of this fault. I'll describe what I did to the power supply and a few other remedial improvements in a subsequent video on this channel. I hope you've enjoyed this video and found it informative and entertaining. Thanks a lot for watching. Have a great day.